I'll try to catch up. Good afternoon. For those that may not know what ISO does, we have three major responsibilities. We are operating the grid, electric grid of New England, 6 New England states, trying to achieve the reliability of the system as a physical system. We're also running the electricity markets as a clearinghouse for, again, the New England territory. And we're also planning, looking 5-10 years ahead. And for this symposium, I thought what the topic might be, and the power system is probably one of the most, if not the most complex artificial system created by the mankind. We are facing all these problems that complex systems are facing, and also the changing in the grid that coming up, and what people were talking before, and Michael, it was a good introduction of what's happening affecting our business. So at the moment today, the system has two distinct separate parts: the bulk power system and distribution system, and they actually are operated as two separate systems pretty much, even though we're connected. But it has each system has its own policies, it has its own reliability criteria, it's operated by two different jurisdictions, and so on and so forth. And what's happening today, and what we call smart grid, we have a lot of new elements popping up in the system as distributed generation, virtual power plants, and demand resources that are not necessarily traditional resources that system operator deals with. And they are sitting on the distribution network and making our system a lot more different than the system we used to operate for more than 5 decades. And the difference is that power system operators are used to operate a system that was a very close perimeter. We knew our perimeter, the system was absolutely known to us, and we know every element that operates on that system. And now today what's happening, a system becomes more open, and our perimeter is not anymore as clear as we have today, and the smart power system and the distribution system kind of merging into one object that we have to deal with. So the question comes, there are two questions I would like to try to talk about this today. How do we face these new challenges that coming toward us? How we architect the grid? Should the grid look differently as we have today? And how we control it? And it is probably useful to look at the evolution of the architecture of the grid. In the beginning, the grid looked like pretty much almost like a set of small autonomous grids, almost like microgrids, had very little connection, electrical connection among themselves, and almost no information exchange among the control centers that operated these separate systems. And what happened is, after a blackout in the 60s, and everybody, I assume, knows about the large blackout in New York, people started realizing that some subsystems could help other systems in terms of reliability. If I have a shortage condition and I don't have enough generation to satisfy my load, I can ask my neighbors to help. And what started happening is the transmission companies or separate power companies started pooling into what's called power pools. The power pools strengthened the links among these different companies and created a very strong grid. There were created a pool control center that communicated with separate control centers in the transmission companies. Still very little exchange among different companies, mostly over the phones. Another side effect of this, another driving force of power systems pulling together was the cost. By dispatching the system as a larger regional entity, we were saving a lot more money by dispatching a cheaper generation in other areas in order to meet the load in the most optimal way. Then when markets created, first of all, the flows among these areas started increasing because people started chasing the prices. So even though we didn't have any transactions pretty much before the markets going on between different pools, now there's more and more power started being exchanged between pools, and the ties here are not strong enough to carry these. And our systems became more sophisticated. We have more exchange of information among different pools, still very little when the markets were created. And then we're now talking about coordinated markets, and coordinated markets require a lot more sophisticated information exchange, and system start talking with each other automatically rather than on demand by the humans. We almost could take some humans out of some of these loops in order to be able to perform certain interregional tasks. The ties are still not very strong among different markets because the transmission investment was not large enough to keep up with these transactions. For example, I can give you an example. If you take TVA, Tennessee Valley Authority, before the when markets started, the amount of transactions going through their territory exploded probably 2 or 3 orders of magnitude. It was hundreds, maybe thousands, hundred thousands of them. So now when we talk about renewable resources, people thinking, how do we architect the system with renewable resources? And there's a lot of suggestions to take and strengthen all these links among different pools and build this very strong, rigid infrastructure that carries wind energy for long distances in order to deliver cheap wind to some load areas. So the question comes up is whether it's cost efficient or not. Is who's going to pay for this? The problem today, the political picture today in the country prevents actually of building these long lines that crossing many territories because people don't want to pay for it. So why would New England pay for wind in Midwest and the building transition, which costs a lot, if it has some wind locally? So there are different questions that we're asking. And also another question from the control perspective, are we building a resilient system if it has such a rigid architecture? If you lose a large transmission line that carries 3,000–4,000 megawatts of power, what do I do? How much reserve do I have to keep if I lose that? So it's not very clear what the right architecture should be. So one of the options is to have a transmission backbone, and we already see these entities coming up and to the system where we have microgrids and virtual power plants, distributed generation, the demand aggregators and PHEV aggregators hanging out of that transmission network. And the question is, how do we build this transmission backbone? The same way as we do today or not? And today what happens is we are building a system which treats reliability as a public good. So everybody enjoys the same level of reliability no matter what. And today when we plan a system, we build it with what we call 1 in 10. It's 1 then in 10 years allowed to lose the load. And it's not necessarily very clear whether we actually are building a system to that level or not, because we don't have enough statistics. Or another architecture where we can split, sectionalize the big backbone into pieces divided by DC links in order to localize disturbances, because if there is disturbance happening in the system, it would not travel through DC links outside of the region. It's not a new idea. It's been around for a long time. But I think what's important is actually to look at this, what the possible architectural solutions are in order to build a system like this. And everybody mentions flexibility, the level of uncertainty that is growing ahead of us. We are talking about implementing so much more wind generation and demand response and some other entities that could act on their own, and we don't know when they're going to respond to the situation and how. So in order for us to increase our flexibility, we need to address it in both planning and operation needs, and we need to make sure that we have a way of quickly responding to different conditions in the system. We today system pretty much built on preventive control paradigm. So we do everything before assuming that anything bad that could happen will happen, no matter what the probability of that event is. And so we always operate system on preventive paradigm. And now we think that we need to start trading off between corrective and preventive actions depending on the situation and system. We're building a system with wider scope that look at system integrity. Besides reliability, we should start looking at some other property of the system that not only make sure that we're reliable, but we also can survive different conditions and have certain resilience. And Michael talked about different new transmission technology that allows us to do things that we never could do before. We're looking at switching to more of a risk-based operation, building wide area monitoring system. We have capability of adaptively islanding the system, trying to localize stability conditions. And Michael talked about transmission switching and some other things that we can run in order to be able to meet the challenges. We also, when we say flexibility, we don't really have a good idea what exactly that means. And so later on, I'll talk a little bit about our attempt to define flexibility in a more formal mathematical terms rather than just waving hands and says that the system should be flexible, and everybody means different things by that. So as I mentioned, we have different challenges that actually to our conventional reliability concept 1 and 10. The system is unbounded. The operator doesn't have control of everything that sits on the network. The contingency definition, and I don't know if everybody knows about it, but contingency is something that we consider the power system, taking certain elements out and see what happens, whether we should have or will have any kind of violation of our reliability constraints in the system, and that's called contingency analysis. And our contingency today is binary. Something is in or out. And it's different from, for example, losing a wind that could disappear within a certain period of time. So instead of just dropping 300 or 3,000 megawatts instantaneously, you can see 3,000 megawatts going away within 20 minutes. And you can't just not react on this, because if it happens instantaneously, we just bring something quickly. But if it goes with certain ramp, we have to follow with generation or other means that change in the wind. And it's not very simple control test. And also, we have so much penetration of computer systems and communication system that together with power system contingency, we are about to start considering loss of certain components of the computer and communication system. And the loss of load definition of reliability becomes ambiguous in some way if you have demand response and distributed generators. We did some studies and we found that it's not enough statistic to evidently or to answer the question whether we're compliant today with today's reliability standards. And we don't necessarily know what that means, why we picked up 1 day in 10 years rather than 3 days in 10 years. And what happens if we relax these reliability standards? And I think we need, we really need some studies that specifically look into this. If you look at the load duration curve that shows how many hours, what percent of time with specific load, system load, the system is operated, and everybody knows that the peak load or a larger, higher load values happen not very often, only maybe 10% of the time. And this is very conditional cut. But if you look at this from the perspective of some peripheral entities that could respond to the prices, that could respond to the condition of the system, the microgrids and virtual power plants and DR could respond to the shortage condition instead of our system being built on the adequacy standards that require our network to fully be responsible for the peak load. And so it is very logical that when the price goes up, the microgrids are going to drop off the grid. The DR would going to drop off the grid and shaving that part. So when we do our capacity market planning, we should be relying on these entities to respond to a certain level of the load instead of trying to build our system fully responsible for the peak load. And it could be, as I said, achieved by the market mechanism. Another property is survivability versus reliability. Not only do we need to know that system will withstand any kind of or reasonable events, we have to make sure that the disturbances that happen and affect our system happen less frequently in the future. So how can we learn when we're looking at the system? And take a look at this one moment of time. And I borrowed this with the consent of from the Software Engineering Institute in Carnegie Mellon. Howard Lipson uses that definition of survivability for the software system. So, but if you look at it, remarkably reminds how the frequency response of the system when you have a disturbance. And if you look at this, it has the disturbance duration and recovery time, and then some time for rebounding, and then the recovery time when you restore the frequency. So the question is, how do we build a system that would respond to different events quickly enough to restoring the service? And if you increase the time between different disturbances that affect the system, it's better. And so the two questions is how we measure it and how we respond to it. And there are different kind of metrics that you can apply depending on how you want to define your survivability, how much time it takes to recover, how quickly you drop or you lose your quality of systems. So there are different actions and operations that you can take and different metrics you can apply on all these different things. I'm not going to talk about each of them for the lack of time. But what's important is what kind of measures we can take in order to respond to disturbances. So there's a lot more actions today than we had before. We can utilize demand response and do our adaptive islanding and things I mentioned before, and transmission switching. But we also we have to plan the system when we design it in order to be able to make sure that we can create a survivable system. And there are four major properties of the survivability that I took from that work from the SEI. And I was trying to parallel what our systems do in order to see if we are working on creating survivable system. And so if you take these four properties, one is resistant to attack, and you can say that we build systems such a way that it would be resistant to attacks. And short-term planning is another process that requires us to make sure that we prepare the system for specific disturbances. And when I say attack, it doesn't necessarily mean it's cyber attack or malicious attack. It could be some kind of, any kind of event happens in the system. And then we have to recognize the intrusion, which means in our terms we have a local wide area monitoring system sensing the system state and trying to prevent, trying to detect if something happens. And then we have to quickly recover after that disturbance happens. And we have our traditional relay protection system, and we have now emergency control system, special protection system, and wide area system integrity protection systems. These are all abbreviations that we use, but in fact these are systems with a larger scope, looking at a wider area of the, and trying to make sure that we guard our system against different events. And also reconfiguration that Mike partially spoke about. There's all kind of different power electronics devices and some other device that allows us to quickly reconfigure our system, not necessarily just the grid, but the system itself. And the fourth part is adaptation and evolution to reduce the future attacks, effect of the attacks. And that's something that we don't do very well. Our system don't have these cognitive and adaptive properties, and I think this is one of the areas that we have to address as the industry. And it is very difficult to try to formalize and measure survivability because it's a property that responds to very rare but high impact events. And everybody knows that actuarial work and everything else is so difficult because of that situation. And so you can see how our system, you can classify different events and different property of the system: stability, robustness, reliability, resilience, in response to exogenous and endogenous events, and also major thing that we have to address in order to achieve survivability. So what is important is to learn from this is that survivability resilience require us to try to early detect the event and then very quickly recover it. If today I can afford, at least it's very expensive, but we still preventively just setting system to withstand any kind of possible reasonable contingency, we can't do it anymore in the future because we have so much unknown and such a big possible set of disturbances that we need to be able to quickly detect it and recover rather than always set it preventively, because otherwise it would be extremely expensive. Also, I talked about flexibility, and we have a problem today. If I want to make systems flexible, both from the design perspective and operation perspective, that means something. I should be very quickly able to follow large changes in the system, and so on and so forth. So you can come up with so many different definitions, and the major objective of the achieving flexibility is ability to ensure that your system could be robust enough to certain range of disturbances in the future. And so we looked at this from that perspective, and we tried to use robust optimization paradigm from this, kind of inversing it. We worked together with Dimitris on robust optimization unit commitment, and we looked at it and said, what if we inverse it and say, can we just you look at this in the same way as a robust problem and saying how much I can withstand of certain range of disturbances, and making sure the system would be completely different within that range. And that make it a metric of flexibility. But there's different determinants of this because it depends how far you look in time. It also depends how large of disturbances you include in considering that, and also what kind of corrective action allowed or not, and the cost. And so all these four parameters kind of playing a role in this, and it determines the space we look into that property. I'm going to skip this, and one thing I want to just discuss before my time expires is that we have to be concerned about the system complexity and vulnerability. We're building a system with many things, moving parts, and we don't know how to measure the complexity of the system and say, are we building a complex system that we can't control? And so what are the ways of making sure that we can actually manage that complexity and not creating a system that's so vulnerable that it's very easy to just blow it apart by very small and simple actions. And so I think we are up to a new control architecture. We have to consider today, we have to start thinking that a very large complex system cannot be centrally planned and centrally controlled, because it's just virtually impossible to have a visibility of a huge, large system. People talk about coordinated hierarchical control, but they really don't have a very clear definition of what that really means. And so we have to start thinking of more decentralized way of controlling the system, and it goes all the way back to Fred Schweppe, that worked with Michael at some point, that had idea of decentralized control. But we have to think of more loosely coupled components of the system rather than building a very rigid control. And also, instead of trying to coordinate this, because then you have to have a central model, we should start talking about cooperating system rather than coordinating. And an example is for if you take a special protection system that balances specific region of a grid, what it can do, it could, and actually when I was way back doing my PhD, I built system like this for centralized and emergency control, which would communicate to the neighbors the maximum imbalance that it could withstand. So whenever I plan my control actions in my subsystems. I'm always making sure that I'm not going to violate any problems in neighboring system. At the same time, I know how much help I can get. And so it's pretty much like ants colonies that really don't have a boss that tells them what to do, but somehow they're marching in the same direction. And we have to come up with methods that actually, in fact, ad hoc in some way. You don't really know how you're going to control in the future. And I think that's the right audience and right new generation of people that should be looking and thinking in these kind of terms to look at the more spontaneous, not pre-planned control actions. And as I said, the complexity should be measured and controlled during design, because we can't build a system that has uncontrolled complexity. And we talked about corrective versus preventive. And that's pretty much it. Thank you very much.